Let's take a look at another region that we're going to be rotating about an axis in order to form a solid of revolution. And we want to decide whether or not the washer or the shell method is going to be easier. So here R is the region bounded by the curves y equals 2x plus 1, y equals 1, x equals 2, and x equals 7. And we want to find the volume of the solid formed by rotating R about the y-axis using both the washer and the shell method. So again, let's work through what this region looks like. We have our axes here. We have the curve x equals 1. Oh, y equals 1, sorry. We have the curve x equals 2 and x equals 7. So let's make one of them blue. X equals 2, x equals 7. This was y equals 1. And then we also have the curve 2x plus 1, y equals 2x plus 1, and that has slope 2 and intercept 1, so it's going to pass right through about here. Great. So if we want to think about what this region looks like, well, we have this region here. And so if I'm drawing these, we're also revolving about the y-axis in order to form this solid. So we're taking these lines and we're revolving them about the y-axis. If we first want to think about which variable would we prefer to integrate with respect to when we're just taking the area of this, well, these vertical lines that I've drawn are pretty nice because the upper bound on the vertical line is always this green curve here, this y equals 2x plus 1, and the lower bound is always this blue curve here at y equals 1. If I were to draw the horizontal lines where we're thinking about integrating with respect to y, notice that we have some differences. So in that sometimes the upper bound, or rather always the upper bound for these x values on these lines is this x equals 7. But sometimes the lower bound is this y equals 2x plus 1 curve, and sometimes the lower bound is this x equals 2 curve. So if I were to integrate with respect to y here, I would run into the problem where I'd have to split this up into two regions. One kind of above the intersection of y equals 2x plus 1 with x equals 2, and the other in kind of this region here below that intersection. So my feeling that I'm getting here is that I would prefer to integrate with respect to x. The second question that I want to answer is which axis am I revolving about? And in this case, I'm revolving about the y-axis. And I notice that my preferred variable of integration and the axis of rotation, these are different variables. So my conclusion is that I would prefer to use the shell method. So the shell method we are hypothesizing is probably better. Maybe we shouldn't say therefore here. Maybe we should just call this a hypothesis. All right, so we have a hypothesis, but we want to actually engage with both of these methods. So let's think about the shell method first. Shell method is going to say take one of these vertical lines and revolve it about the axis to form a shell. So we're integrating with respect to x here. The left endpoint of my region is x equals 2, and the right endpoint is x equals 7. In order to find out what the integrand should be, I want to think about what the surface area of one of these shells is. I know the radius of a given shell is the x-coordinate, so its circumference then is 2 pi x. The height of a given shell is the y-coordinate on the green curve minus the y-coordinate on the blue curve. The y-coordinate on the green curve we know to be 2x plus 1, whereas the y-coordinate on the blue curve we know to be simply 1. Great, so we have our integral set up. Let's go ahead and do the computation. We want to factor out the 2 pi. we're going to have, I know that I can cancel out this one and this one, so I've got a 2x inside the parentheses here, which is going to allow me to factor out another 2, and so this is actually going to be a 4 that I can bring out front. Left inside of the integrand, I have an x squared. Cool. Easy integral to do. This is going to be 4 pi x cubed over 3 evaluated from 2 to 7. And plugging in some numbers here, I'm going to get 4 pi over 3 times 7 cubed is 343 minus 2 cubed is 8. And this, if you crunch the numbers, is going to give you 1340 pi over 3. Lovely. So our shell method was nice and fast as we predicted, but let's compare it to the washer method. If I'm working with the washer method here, this means I'm integrating with respect to y. And as we noted earlier, because I have different upper bounds and lower bounds on y as I change y, I'm going to need to split this up into 2 different integrals. We're also going to need to know some y values of some of these intersection points. So let's note that the y value of this intersection point is when I plug in 2 for x into y equals 2x plus 1. So that's the y value 5. And the y value of this other intersection point up here is going to be when I plug 7 into 2x plus 1, and that is going to give me 15. So I have my y coordinates here, and that tells me that in order to do the washer method, I need to integrate from y equals 1 to y equals 5, and I need to add an integral from y equals 5 to y equals 15. So on the interval between y equals 1 and y equals 5, I think about the upper bound on my x values here is this green curve at x equals 7. So what I'm looking at here is, we have washers. Washers have surface area equal to pi times the outer radius squared minus the inner radius squared. So pi times the outer radius, well, the outer radius here is simply 7. So we have pi times 7 squared, minus the inner radius. Well, this is also pretty nice. The inner radius is actually just the constant 2. So I'm integrating 7 squared minus 2 squared dx. That's going to be a pretty easy integral for us to do. We'll come back to that here in a second. Let's set up the other integral. So between 5 and 15, I'm looking at the upper bound on y, so I'm looking at kind of this region here. The upper bound on my x values, rather, are at x equals 7 here, so that is still pretty straightforward for us. Unfortunately, I've colored both of these curves green. Oh well. So we have 7 squared as the upper bound for x here. The lower bound comes from the x values on y equals 2x plus 1. So I need to solve for x here in terms of y. So if I have something like y equals 2x plus 1, y minus 1 is 2x, and that is to say that y minus 1 over 2 equals x. So my x values on this left curve are y minus 1 over 2. So we want to use that as the x value here, at y minus 1 over 2. And again, we're squaring the radii of the circles for these washers here. Oh, and this first integral should have been with respect to y. Great. All right, so a little bit more painful of a setup here, but still we're looking at some pretty manageable integrals, so we can actually do these computations. So let's see, 7 squared minus 2 squared is 45, so I'm integrating 45 pi here, and what I get out from that is 45 pi y evaluated from 1 to 5. The second integral is a little bit trickier. I think maybe it would be easiest if I did a u substitution here. I'm going to let u, let's draw a better u equal y minus 1 over 2, so that du is dy over 2, or in other words, 2 du equals dy. So this integral here, if I use y equals 5, I'm thinking about my limits of integration here. So if I plug in y equals 5 into here, I'm going to get 5 minus 1 is 4 over 2 is 2. So 2 is my new lower bound of integration. If I plug 15 in for y, I get 15 minus 1 is 14, over 2 is 7, so 7 is the upper limit of integration here. I still have pi. 7 squared doesn't change. That's still 49. Fortunately, I can substitute in u for that y minus 1 over 2, so I've got 49 minus u squared here, and dy is 2 du. Cool. So now we can actually do this second integral, and we can evaluate the first term. So this 45 pi y evaluated from 5 to 1 works out to be 45 times 4 times pi, and 45 times 4 is 180. So we get 180 pi for this first term here. For the second term, let's see, we can now integrate. So this is going to be pi times 49u minus u cubed over 3. Oh, times another 2. And I want to evaluate from 2 to 7. All right, so we have a little bit of arithmetic to do here. So we have 180 pi plus 2 pi. Evaluate at 7. 7 times 49 is going to be 343. 7 cubed, also 343. And I want to subtract evaluated at 2. 49 times 2 is going to be 98, and 2 cubed is 8. All right, let's keep going. So let's see, we have 180 pi here. We have plus 2 pi. We're going to have 343 minus 98 is going to work out to be 245. Minus 343 over 3 plus 8 over 3 is going to work out to be a minus 335 over 3. We want to convert everything into thirds so that we have some common denominators here. So we're going to have 540 thirds times pi. We're going to have 2 pi, 245 is 735 thirds, minus 335 thirds. I'm not doing these computations in my head, by the way. I have done these computations ahead of time, and I'm just reading off of them. This is a little bit too much mental arithmetic to try to do while being recorded. All right, so let's keep simplifying here. 540 pi over 3 plus 2 pi times 735 minus 335 is 400. And now I notice that I have 540 pi over 3 plus 800 pi over 3, and that's going to give me a neat 1340 pi over 3. So zooming out again to do our comparison here, we notice, yep, I got the same answer using both methods, and that is great. 1340 pi over 3. We notice that my hypothesis was confirmed again. The shell method is probably better. Yeah, the shell method's a lot better. Again, neither of these integrals was particularly hard to do. We didn't run into any tricky u substitutions, though we did have a u substitution in our washer method here. But the region was much nicer when we were integrating with respect to x, because we only had to do one integral, whereas we had to deal with two integrals when we were integrating with respect to y. So we can see that these guidelines, at least for these examples that I've constructed for you, are working so far. In the next video, we'll take a look at another example where one of the methods is not even going to be possible for us to do. So maybe I'll let you try that, and we'll see how it works out in the next video.